Hello, I'm Wenqi from Yat-sen University, China. Today we will present our project, Cooperative Control and Experiment for Multi-Robot Assembly of a Solar Power Satellite. The solar power satellite, like SPS Alpha and Emma SPS, is an extra-large and complex spacecraft. It cannot be launched directly into space. Therefore, modular design and in-orbit assembly become a viable solution to construct it. Consider an antenna module. Such modules can exceed several meters or even tens of meters in size. How can we construct such large structures in space? The answer lies in in-orbit assembly technology. Given the mission's large scale, vast distances, and extended duration, it is difficult to rely on humans or a single robot for the tasks. Therefore, a collaborative approach involving multiple robots is essential. However, research on multi-robot in-orbit assembly is still lacking. In our mission, we identified two types of robots: the crawling robots, which are battery-powered and without propulsion system, making them ideal for long-duration tasks, such as docking and assembly modules. The flying robots, which are highly mobile but limited by propellant consumption, it is suitable for module transportation. So this is our project, Multi-Robot Collaborative Assembly. These robots will collaborate to complete the assembly mission to achieve reliable and accurate in-orbit assembly. However, this project faces several challenges. The first challenge is how robots collaborate. The key point is trajectory planning. Our target is to assemble the U-shaped structure shown in the figure into a square antenna structure. First, the flying robot transport the module, and following, the crawling robots work together to assemble it. And due to the size of such modules, relying on a single robot on one end can lead to significant deviation at the other. To counter this, based on forward and inverse kinematics, we propose a collaborative trajectory planning strategy. During assembly, the crawling robots must adapt to each other's movement to meet cooperative constraints. The relative motion of the robots is kinematically restricted by the constraints. However, real-world executions always introduce error. So how can we ensure the accuracy and safety of the assembly? To address this, we design a cooperative controller. When collaborating, the robots need to observe each other's actions, and you can see the structure of the controller. They should not only follow the planned gate, but also adapt to each other's movement and to reduce the endpoint deviation. This prevents large internal stresses in the structure to keep it safe. The detail of the controller is this. It can be divided into two PD controllers, where Kp and Kd are proportional coefficients. E theta j is the trajectory tracking error, E theta cj is the cooperative error, and C represents cooperative. The first two terms of the equation ensure the tracking of the planned trajectory, while the last two terms solve the cooperative trajectory through inverse kinematics. And this trajectory will rely on current robot motion, and these two terms could perform fault tolerance. Here's the simulation result. You can see in the GIF. Consider the fault scenario. The joint of robot 1 will fail in the 5 to 10 seconds after grasping, which means it cannot apply torque at that time. This will result in structure deviate from its planned trajectory shown in the green line. In this case, the other robot cannot continue on its predefined path. It must adjust the failure to avoid damaging the structure. Our controller is designed to handle such scenarios, demonstrating its high robustness to ensure the safety and in-assembly process. And you can see the figure here. Compare non-cooperative control methods in orange line. The error of our controller, which in blue line, is significantly reduced endpoint deviation. The fault tolerance ability demonstrates strong robustness of our controller. And here's the detailed data of the robot angle. You can see one of the joints will deviate from the planned trajectory. Then the other robot adjusts its movement to minimize deviations. To validate this work, we also conducted a multi-robot assembly experiment to further validate our project. In this experiment, we use a robotic arm to simulate a flying robot to transport a module. While the two crawling robots will work together to assemble it. As you can see, the two robots cooperatively grasp the module. The robot movement will excite structural vibration, which poses a risk to the assembly. Then, the robotic arm releases and hands over the module. The two robots work together to complete assembly. And you can see how they dock in the module. This experiment demonstrates the feasibility of our project. In experiment, we use a camera measurement system to observe the position of the structure, so that we can plan the cooperative trajectory to control the robot. And you can see how the camera detects the tag to obtain the position of the module. In conclusion, to devise a reliable and automatic in-orbit assembly, we have tackled the challenges from both theoretical and experimental angles. We developed a cooperative trajectory planning method to meet the collaborative constraints. We designed a cooperative controller, which robots can adapt each other's actions, and its fault tolerance ability and strong robustness can keep the safety of the assembly execution. Finally, we'll validate the feasibility through experiments. We also designed a special part for this interactive presentation. We designed a very interesting web page so that you can use this web page to control the robot. You can see, touch the slider here. And you can see the preview on this web page. Then submit. And the robot will follow this instruction to move. And you can see how they move. So that's all. Thank you.